Hey everyone, we're going to take a look at number 5 in section 4.7, again on optimization. This section is, and this problem wants us to find two positive, I've underlined that, it's important, two positive real numbers x and y, such that their product is 1250, and x plus 2y is as small as possible. So we're looking for what? A minimum, right? We're trying to minimize this function, really, which is a function of x and y. Okay, so they do give us the variables x and y. That's good. So when we talk about their product being 1250, we know then x times y is 1250, right? That's the given information. And I can solve for either x or y. In this case, I chose to solve for y by dividing by x, right? Both sides. And of course, this is true as long as x is what? Greater than 0. Again, we're not including negative numbers, right? And we know, of course, x cannot be 0 because, again, the product is 1250, and you can't multiply by 0 and get 1250. And so that's important from this fact here, right? That x is greater than 0, because x could be a negative without that. If we don't say positive, then x could be negative. Okay, and y would be, of course, negative as well. And then that would we can make this really small based on negative values. Okay, so they are positive. That's important, and I'm going to let this sum here, x plus 2, I'm just going to call that s, so we have the name of a function. S equals x plus 2y, so we can just call that the function we want to what? As small as possible. As I said, this is a minimize this function. Okay, so we need it to be a function of one variable here, and so since I've solved for y, I can replace y in this function with 1250 divided by x, and that's what I've done here. So s is just x plus 2 times y, which is this. Cleaning that up, I get x. 2 times 1250 is 2500. 1 over x is the same as x to the negative 1. I like to write it that way because I am about to take the derivative. And again, x again is positive in this. So we're trying to minimize this function on an open interval. So it's real important on optimization problems. Are you operating on an open interval or a closed interval? If it's a closed interval, you're doing what to show you have a max or min? Checking the value of the function at what? The endpoints and any critical points, right? And whichever one's biggest is the max, whichever one's smallest is the min. Here, though, we have open interval. I can't check any endpoints, so we're going to have to use the first derivative or second derivative test to verify we have a max or min, and check that it indeed is the max or min on the interval x greater than 0. Okay, so we take the derivative of this function. Derivative of x is 1. Here, 2500 is a constant multiple. Power rule, bring the negative 1 down. Subtract 1, we get this. And I can rewrite this as 1 minus 2500 divided by x squared, right? X to the negative 2 is divided by x squared. So I want to write this all over one common denominator. 1 is equal to x squared over x squared. So now I can subtract x squared minus 2500 over x squared. So there's my derivative. It's never undefined because remember x is always greater than 0. So this, we're never dividing by 0. But the numerator is 0, right? When that's 0, that will make the derivative 0. And that happens when x squared minus 2500 is 0, or when x is the square root of 2500, which is 50. Okay. Now we're not done. Some of you are just saying, oh, well, x is 50 and I can find y and I'm done. You have to show that you have a minimum. This is just saying that the derivative is 0. If the derivative is 0, you could have a maximum, right? Right up there, the derivative could be 0 to max. You can have a situation like this where you don't have a minimum or a maximum. You've got to make sure it's this, right? And how do we do that? We do it with either the first or second derivative test. I'm going to use the first derivative test, and that is doing what? A sign check on the first derivative. It's everything greater than 0. We know at 50 it is 0. If I plug in something less than 50, say 1, if I plug in 1 here, of course the bottom's 1, I get 1 minus 2500, which is a negative number, and so we get negative for values between 0 and 50. If I plug in something bigger than 50, x squared will be greater than 2500, and this difference will be positive. So we have what? a change in sign from negative to positive, which means the function is going from what? Decreasing to increasing. So we've got this sort of situation here. We've got a local minimum. In fact, I know it's a global minimum because on the domain, we're decreasing to 50 and then we're increasing forevermore, right? So this is the actual minimum, absolute minimum on the interval for this function. Occurs at x equal 50. Now we can say y is what again? It's 1250 divided by x being 50 in this case, and we get 25. So these are the two numbers, two positive numbers, right, whose product is 1,250, such that the sum of what? X plus 2y is a minimum or as small as possible. Okay, very important though, you show the support. You could have also showed the support by the second derivative test where you took the second derivative here and then, right, you plug in 50, and using the second derivative test, we can tell if the second derivative is negative at that point, at any critical point, which this is, then we have a local maximum. If the derivative is positive, then we have a local minimum. If the second derivative is 0, then we would have to go back and use the first derivative test. So okay, either way is fine, but make sure on the test you do show that support. Okay, hope this helps on number 5 from section 4.7.